Yeah, okay. Everybody over there, wherever. Okay, okay, good. Okay. I mean, I don't know whether you know that historically, John Byers and I were arguing what this conference should be named. And I was pushing compositionality, and then John was pushing applied category theory, and the compromise was the journal is compositionality, and the conference is applied category theory. But here, this is compositionality as the origin of quantum mechanics, put forward by Schrödinger. Nobody took notice of that until a little bit over 20 years ago, about that paper, when quantum computing came and the importance of entanglement in quantum computing was started to become realized. So then, and Samson here too, you could call the categorical semantics of quantum protocols in Leaks 2004, you could call this Schrödinger's view from the world of categories. You start with formalism, trying to make quantum fundamentally compositional. So that's kind of what we did in this paper, and we got the Leaks Test of Time award for that one. Clap, clap, clap. Samson is here too. Yeah, they do this 20 years after the paper. I say, okay, that paper was actually no crap. So anyways, right? This is Roger Penrose here in Maths in Oxford. As many people in this community, of course, know. Maybe don't know the history. As an undergraduate student, he didn't like the notation of general relativity, and he started to use this kind of symbols instead in the context of general relativity. This was only publicized in one paper in some appendix, and then in the 1990s. Joel and Street started to take this seriously and showed this was actually an equivalent formulation of certain normative categories. So suddenly these diagrams got a status as a mathematical entity in the traditional sense. As far as I'm concerned, they were always a mathematical entity, maybe less traditional. Now we know we can translate them in traditional language too. And 2005, I mean, this paper, Categorical Semantics of Quantum Protocol, was very well received by the computer science community, especially the semantics type community, like MFPS and this kind of people. Physicists didn't like it because it was why should we learn category theory? So then you can use these diagrams, and I published this paper. It was like a tongue-in-cheek towards them, kindergarten quantum mechanics. Which basically was the same paper as the one before, but just with string diagrams instead of like more category theory language. Right. In 2009, I wrote another paper called Quantum Picturalism, which was commissioned by something called Contemporary Physics. They actually paid for your papers, by the way. So it was the first time I got paid to write something. And somewhere, because it was very frustrating how negative the mainstream physics community was, quantum computing community, to this word, and without even knowing what it was about. So I said, I'm going to prove them wrong, and I suggested an experiment, an identification experiment, to make them all look like idiots. That was 2009. After 15 years of work, anyway, most people know this book here, Quantum in Pictures. Took 3 years of Aleks and me writing, and I don't know who came out the oldest after this. I think Aleks. Aleks sort of suddenly became older than me by having to write this thing with me. Anyway, so then I started serious think of doing this experiment, and we needed a book for the experiment. And the experiment now is about trying to teach teenagers quantum using diagrams. That was the general goal. So I wrote a new book with Stefano, and this was mainly intended for this experiment as a tutorial. Of course, it became a thing in its own right. And on the back, you can read, maybe you think you don't know, hello there, I want to learn some quantum, maybe you think you don't know enough maths. Well, that's not a problem. The pictures in this book are a new kind of math that will teach you all about the quantum world. And I'll give some examples later about the stuff we treated that. But it's pretty much a full-blown quantum computing course. The only thing we don't do is quantum algorithms, for the reason that the formulation of the problem itself alone already requires like high level of mathematics typically. So you simply can't even state the problem for a broad audience. Well, that's not really true, because simulation, there is no problem stated. You run a quantum process on a computer, and of course that's here. Okay, quantum picturalism, the experiment. So that's what we did this summer. Like I said, I proposed this in 2009. I think we started to work on the tutorial. I mean, I don't know whether you remember. It was just immediately after the Dundar book, right? Pretty much, I think. So 2017, 2018, we started to write tutorial. Then it was just so hard to get any funding for this. Just to get personal pay, because you need different kind of qualities. This is not a small scale experiment. You need a lot of people in that. You saw all the names on on the thing. And then, so it was just impossible to get funding for it. And so ultimately it was paid for by Continuum, my company. And then in collaboration with the people at Oxford University who were just there, like Aleks and Stefano, they were all employed there, so they could help with that. Anyway, so we did it this summer, finally. Ethical approval took a year. A year to basically being allowed to do that. Right, so we wrote a book, then we also, again, there was a lot of effort, some money, then we made video lectures of the entire book. Usually I've got like prizes to give away, so but I already gave them away before the talk. So I'm still going to do a little quiz. What am I explaining on that? Only non-physicists can answer. Nobody knows it. Yeah, of course. I mean, you got the course. Yes, I mean, this was the first proper use of string diagrams applied. First ever. Picture of quantum teleportation. This goes back to 2003 even at some point. So that was the first applied use of string diagrams, I think. I may be wrong. No, well, no. There is the trace of Samson was talking about yesterday. So that also was in pictures. That's true. So, but this was like very concretely applied going back to 2003, immediately after the physical traces paper. Okay, so then we also did exercises. So basically what we were doing is we were entirely mimicking the structure of an Oxford University postgraduate course. That's what we were doing. We were completely, it takes 8 weeks, which gives you some lectures. So we had these videos, then you get some take-home exercises. So we gave them exercises, and then I did the solutions. Like it was all pretty horrible because everything was online. Everything was online. Ethical approval forbid us from basically using any social media. So these kids were not able to talk to each other via Discord or anything like that. They were not able to talk to each other, and there was lots of anonymity conditions and stuff like that. So it was horrible. As a teaching experience, it was horrible. Then this was like a COVID generation, and what they call Generation X or Generation Z. What is it again? Z. So these people, they just stare at screens and they don't talk. And effectively, we had tutorial sessions, and these were just blank screens. And then a few people asked questions, but they typed them. So there was no human interaction whatsoever during the entire course. I, in the middle, as my collaborators know, I was going to basically pull the plug. They said, this is going to be a disaster. You can't teach it, you can't see faces, you know. I wrote a really aggressive email, not aggressive, but it was polite, but email to them, and then one person put on the screen for like 3 seconds, and then they put it off again. It's true. Caterina, it's true. Anyway, so we did this. With this course, we basically did a call. We had a flyer. I could have shown this here. We had a flyer. We got 1,000 applications from the UK. Again, for ethical reasons, this could only be UK. Then we pretty much randomly selected 60 out of them, of these 1,000, just to make sure that we had a nice distribution of good students and also good students. That was like nicely distributed. And then at the end, we gave them an exam. We basically, what we told them is like, we give you a course for free and everybody gets a certificate. Everybody. Doesn't matter how good or how bad we do, everybody gets a certificate. Then at the end, we did ask them, okay, for our study, can you please try to solve this exercise? And this was an exam entirely consisting of Oxford University postgraduate quantum exam questions. Those were the questions. They were all taken from postgraduate exam. No? So 50% of the kids got distinction, which is higher than your typical average you get for an Oxford University postgraduate course. And tell me if I'm wrong, because we haven't got a paper really with all details, but the younger kids did better than the older ones. Younger kids did better than the older ones. And I don't think that's a matter of motivation. I don't think that. We still have to investigate better, but I don't think it's a matter of motivation. So we didn't have a paper. This appeared in the Guardian in not that many people saw it because it was just before Christmas, like a bad time. So they did a whole page. They did a whole page about our results. This is science journalist who I happen to know. Personally, she knew we had been doing this for years. She had these, do you have results? Do you have results? Okay, see, I've got results. Okay, I got it. So there was the blog post where you can already read about it. So again, you see the names of all the people who were involved with it. And now it's your turn. So the way this, I'm just going to give you an idea of how we teach them. I know a lot of people know this here. So we typically use string diagrams, wires, and boxes, as everybody here, assuming the audience knows, is familiar with. This is Schrödinger. You compose them. Your basic ingredient in your language is composition. Where you see at the right bottom 2 wires side by side, that's a tensor product. That's what Schrödinger was talking about. Putting 2 things side by side. That's all he was talking about. Here, this is like putting 2 wires side by side, nothing more. And then the conceptual thing is like this teleportation stuff I talked about, and I showed that was all done with wires. The idea is we have to move to something rich, which we call richer, which we call spiders, but then in fact they're generalized wires. So what is a wire? A wire is a thing with 2 endpoints, right? And what is the behavior of a wire? If you compose 2 wires, you get another wire. So this is like an extension lead or something like that. Huh? So okay, this is spider. We just call them spiders because we don't want to call them dagger special commutative Frobenius algebras. This is what you have to write in your computer science papers, otherwise you don't get accepted. If you call them spiders, they don't accept you. That's it. So what is the behavior of a spider? Well, same as a wire. You put 2 spiders together and they give you a spider. Yeah, it's only the legs, you have to do some accountancy of the legs, but that's all. It's pretty much the same. Now, to get a universal language for quantum, you need 2 kinds of spiders. And this corresponds, say, with position and momentum in quantum mechanics, like complementary observables. And they don't like each other, so they each give each other some sort of uppercut, and then their leg flies away, because spider legs are sort of fragile. And so whenever you see 2 wires between different colors, they fall away, they go away. Right, so 2 rules. Fuse, same color, 2 wires between different colors. This is quantum program. The vertical lines are 3 qubits, say. 3 qubits. The horizontal line are gates which you apply to the qubits. And they happen to be, if you translate them to Hilbert space, C0 gates. So very, very standard computational gates, and they're made up of these spiders. So now we start computing, and in any other audience, I ask the people what comes next, and then they get a prize. Now, in this audience, it's a bit stupid, because I think so many people are so familiar with this stuff, so I'm not going to ask it. I'm just saying, well, okay, you can say it still. So what's the first thing you do here? Huh? Well, come on, you were my PhD student. Somebody I don't know. Somebody I don't know. Anyway, he said it. You fuse all these colors together, like that. You know, if you ask the same question in a room of physicists who've not seen this stuff, they have a complete mental blockage of doing that. Because they think of these CNOT gates as monolithic things, and they now turn in something that's kind of meaningless, that very hard to pass what it even is, something they don't know. So they would never do that. They would never do this naturally. The kids, of course, they just do that. Of course they do that. No? Okay, next thing, 2 wires go away, and then this is just tied with 2 endpoints, so that's just a wire. And so what I just did is effectively the state of the art in quantum industry on how you simplify a quantum program. This is state of the art, and for example, Ross Duncan, who people know, who's like co-invented these spiders with me, is leading our software team in Cambridge, and this is implemented in our compiler. And also at IBM, they're using this for optimization, and at Google, they're using this for optimization. So all the big firms are using this now. And I'll give some more example later. The sort of more interesting conceptual stuff is when you start to basically mix up quantum and classical. So what you got here is going from quantum to classical. So that's the measurement. That's von Neumann's thing. That's the thing von Neumann thought was the most important ingredient of quantum mechanics. Measurement. It's going from quantum, which I now represent by 2 wires. But anybody knows quantum formalism, this corresponds with how you do density matrices. Again, from von Neumann, you take a bra and a ket and a bra, so you pair them. And that's exactly the same as this doubling. I mean, we explain all of that in detail in the Dodo books, like where this comes from in relation to the usual quantum mechanical formulas. And this effectively gives you a measurement. You go from quantum stage to classical stage. Now you can start computing with them. So at the bottom, I've got the opposite. You go from classical to quantum. I've got a bit, and I encode this as quantum bit, for example. And then I measure it. And then by my fusion, I know I'm doing nothing. So it's a stupid thing. Now, of course, if I change the colors, I've got one color where I encode, and then I measure the other ones. The 2 wires vanish. You saw no wires on the right-hand side between, which means those 2 things have nothing to do with each other. Whatever comes out at the top is actually randomness and completely unrelated to the bottom. And that's because these measurements are incompatible. Now, this, I think, is the most beautiful example. So you see like on the left-hand side, you got like these two coming in, two coming out, and then also a single one coming out. So I got a quantum system, I measure it, I still have the system, but I also got some observational data. So I observe in one variable, then I observe in another variable, and then I again observe in the first variable. And as you see, the first observation of one variable has nothing to do with the last observation of the same variable. And that's because, of course, this intermediate measurement changes the state of the system and puts it in a state which is completely unbiased with respect to the first variable. So you get randomness again. So this is conceptually deep stuff. You don't need spectral theorem. You don't need all of the stuff which you usually need to complete this. You do this just with these spiders. This sort of idea of representing classical and quantum like that goes back to a paper with Dushko Pavlovich and Eric Packet. So that's where we start to use this double single stuff. Pretty much at the same time as the two called spiders with Rosberg came out. Let me check the time. Oh yeah, I'm fairly good at it, because I'm not going to say that much. So this is the kind of Swiss Army knife of our calculations. It's called ZX calculus. I think there will be later talk about ZX calculus by Boldi, right? Yeah, by Boldi. So the thing at the bottom left, you see that's a square. We call this square plotting. So you got a square. So suppose you get like there a square. How do you get rid of a square? But that's the rule how you get rid of a square, and you can reduce with line. Now people would usually write is completely different because it's like bialgebra. So this is basically a monoid and a comonoid communing to each other, but this is much more useful in the context of reading the pictures. Now, I mean, I'll give you a proof of quantum non-locality. That's the stuff Sieglinde got the Nobel Prize for in 2022. So when you got here, you see, you got 4 scenarios. You see these 4 pictures side by side. There are 4 measurement scenarios where you take a 3-system state, because you got dots at the bottom with 3 double wires coming up. These things on top are measurements, different bases. So you have 4 different scenarios where you measure 3 systems in different ways. Now, I'm going to sort of do hand waving, we do the calculation, but because of the bialgebra thing, about the green and the red commutes. I mean, this goes back to papers, like nice papers by Steve Leck. Steve Leck wrote about that stuff. So you commute the red and the green to each other, and then you can just fuse all the green dots. And you see there's angles on some of these. So the angles actually just add up. And you see if you add them all up, you get underdating. So you would end up at the top with like a red dot underdated, which is actually bit 1. Turns out this is bit 1. This is the expression that you get a local relativist theory. Basically, what you're doing is for every measurement in one of these scenarios, you assign a predetermined value. This can be probabilistic, it's no problem. You assign a predetermined value, and then you sort of this spaghetti is basically distributing them over all different scenarios. And now you see that between the green and the red, there's 2 wires always, so they fall away. So on top, you get like a red dot without a. Basically, this means 0 and 1. And 0 is not equal to 1, so you get a contradiction. So quantum mechanics cannot be explained in this way. Can't be explained in a local realistic way. Okay? You say, in principle, you don't even have to say words. Everything is in the picture. The whole argument is in the picture. Right. Why is it important? We need quantum workforce, and this can't just start at the university level. Quantum picture moved away like 2,500 years of old scientific tradition. That's a big statement, but it's true. So all of physics, as the way we know it, which typically is first you present kinematics, then you present the dynamics. The kinematics is a static picture. The dynamics takes you from one picture to the next picture and the next picture. That was a proposal by Parmenides, one of the pre-Socratics, who thought we are always living in a picture. And there is only the now. Heraclitus that was different. He said, like, no, there is never a now. You're always going from the past, from what was, to what will be. It's becoming. So Parmenides is being. Heraclitus is about becoming. These process pictures I showed, it's always about becoming. It's processes. There is no static thing. And then another thing, Democritus told us we need to understand things in the way they are made up. Atomism. Leibniz, no, what's more important is how you relate to each other. And this whole compositional framework is about the relationship between the different things. So this is a big departure from Western scientific tradition. And that's why the younger kids probably are easier with it. The less maths they know, the easier they are with it. Because relationism is a very natural human thing. We relate to each other, you know. We're not always talking about what's inside of it. We relate to each other. So, and we're constantly in a process. And because when we stop being in a process, we're better, we get better. Right? So people need to get used to this at early age, what I was saying, before being indoctrinated wrongly. Stakeholders need to know what's going on, contra what fuck up which is going on in AI. Nobody knows what the fuck is going on. But I say, Nobody knows what the fuck is going on. Fabrizio, everybody wants to hear you swear.
Yes.
This guy used to say fuck 10 times in every sentence when you do my PhD, Steve. You make up later, okay, that's good. There's also an opportunity to make STEM education research more attractive. What was important when we asked these kids, what do you think about this? They didn't say we learned a lot necessarily. They didn't say blah blah. They said it was fun. They loved doing this. It was something they enjoyed, like a game. Okay, perfect. It was something they enjoyed, which is really important. So what's going on now? In Greece, we have governmental approval and a translation has been made to start teaching quantum using our book and stuff at high school level. That's going to happen in October already in Greece. So Elevate Quantum is a consortium making up New Mexico, Colorado, Wyoming. They are sort of trying to be now the Silicon Valley of quantum. Like, because they have so much concentration of quantum companies. Lots of companies are moving from Silicon Valley there, by the way, because of tax reasons. So they're like, and they have like this manifest, how they want to become this, and very much on the front, they're going to use all this stuff for work for the generation. So they use like our thing for work for the generation. Colorado, Denver, the schools are also going to start to adapt this. A certain region of schools, they're starting an exhibition in the main sort of science museum there, so they're pushing it. The White House, there is now a joint federal office of many funding agencies, and they want to do a very broad thing with us to basically study demographics of this thing, to then possibly install it as much as they can, because it's a state, it's a bunch of states, like at a national level. So this is really happening now. Quantum is being taught, it's going to be taught at high school level using this. So this is applied category, properly applied. Yeah, and there's lots more on the way. Okay. Last thing, like, this is not just education. In industry, I don't know who knows the guy named Peter Shor and what he did. He's the guy in factory now. Yeah, he's the father of quantum computing as an actual thing. So he's now advocating the calculus for anything to do with error correction. And he's the father of error correction, by the way, quantum error correction. Here's another paper from PsyQuantum. You know, this has taken 20 almost years since the beginning of quantum, well, no, not 20, say 50 years in the beginning of category quantum mechanics before people started to even look at this EXPO. Now, every photonic quantum computing company is using it as their main language, because Hilbert space simply doesn't work there if you work with light. It simply doesn't work to describe things, and this has to do with the manner in which they measure. They observe. They have a big entangled state, and they observe stuff. They don't run a circuit. And that's super complicated to describe in Hilbert spaces. I think that's about it. That's it. That's a good end. And yeah, that's a good end.
Thanks, Bob. It's time for a few questions, but I would already like to ask the next speaker to come forward. Yeah.
When you optimize the quantum circuit in the ZX performance, are you able to do any space where you just
He's doing that stuff.
And it's all heuristic stuff.
You get various things. We don't like that's how to take one file. What? We'll see.
Yes, please speak up.
So this all works for sort of the programming of quantum computers, but do you have any work for designing quantum computers, which normally uses like infinite dimensional Hilbert space to model the actual physics?
Physics. I mean, that's very bad use of word physics. I would say, is it okay for you?
Yeah,
physics. What I talked about is physics.
Well, okay, it is,
Okay.
but it's sort of the engineering of the quantum.
Yeah, so I
computers,
think we get talks later this afternoon about what's called Q-Finer. Fabrizio has worked on diagrams in quantum field theory. So these things are not as developed yet. They're very much in the making. Very much in the making. And then we got something which is called ZXW calculus. I mean, that can differentiate, integrate, exponentiate. So we're working with chemists literally on like solving differential equations. And that's what you mean by real physics, I think. Yeah, we're doing that stuff, yeah.
Very good. One more question?
Yes, please.
So I'm interested in what the methodology of the experiment was. How did you find the students? Did you have any kind of?
I mean, this was the first pilot experiment, so we basically just did a call. We sent flyers up, schools, we just sent a whole bunch of flyers up. Like I said, we got like 1,000 responses. It wasn't ideal because people were finding something like that. We were doing this in May, June, when people had to take the A levels and stuff like that. There was no lot in the summer, but of course, many would have gone on the holiday and stuff like that. So it wasn't ideal at all as a technology, but we just wanted to get it done as a first pilot, which was a good thing to do because it's already moving. But now, for example, with the White House, they want to do it properly. They want to do it properly to really see what is the potential in this. Okay.
Okay, very good. Thanks again.